for joining us for this first video in chapter 12, or where we start talking about the reactions of alkenes. In the last, well, chapter 11, I think, we summarized how you can make alkenes, and then here we're gonna just start discussing what you can do with them. So throughout maybe chapters 7 through and on, we talked about many different ways you could make alkenes. I say many, but they all have to do with the elimination reactions, basically either E1 or E2. Now, there's a couple other reactions that do result in alkenes, but that's going to be for the future, mainly in the spring semester, I believe. But yeah, so with these, we can actually start to do some serious synthesis, like an actual organic chemist who has to design the synthesis of many things. So I hope you're excited about that. Now, especially in this chapter, you should be able to see the recurring themes. Which, by the way, we're not covering this in this semester. So sorry about that. I meant to take that out, but the recurring theme is going to be that they're going to be all addition reactions. And I don't know if you remember, like, the different types of reactions we covered back in chapter 2 of the semester. But if you have some sort of generic double bond alkene molecule, and you add this generic molecule made of two atoms, A and B, those are just hypothetical atoms, they're going to add across the double bond. And this is what we mean by addition reactions. The first one of those is going to be hydrogenation reactions. This means you're going to add H2 or hydrogen across a double bond. The key idea that it's going to happen through syn addition mechanism. And right here, that, by the way, just means same side. It does. There's nothing wrong with syn addition. It's not the SIN word. Okay. Now, what does that mean? That means the two atoms add from the same side. And this is the typical setup. I want you to know a hydrogen molecule, that's usually a gas. Often these reactions are done with just a balloon filled with hydrogen gas attached to the reaction vessel. And then in the reaction vessel, you might have a solvent like ethanol or ethyl acetate. Those are fairly common. Palladium on carbon is the common catalyst for this. That just means that palladium powder is very fine powder. So like when you handle it, it's kind of dangerous because it just goes into the air because it's so fine and it goes everywhere. So what they do is they deposit the palladium powder onto charcoal powder so that it has more weight to it and it's more dense, and that's what this means, palladium on charcoal or carbon. Okay. I might also point out that, like, in the textbook or something like that, you might see the use of platinum catalyst. Either way, these are all both catalyst. Okay. And the product is going to have the two hydrogens added from the same side. So maybe we could draw it like this. Now, you might wonder, well, they add from the same side, but how do you know it's from the back side? Well, I don't, but notice for this specific compound anyway, it doesn't matter which phase of the molecule it adds, because I want you to notice how there's a plane of symmetry, this product. So this is a meso compound, and so for that reason the stereochemistry kind of doesn't matter, or the facial selectivity doesn't matter. But if there was no plane of symmetry here, the product would be racemic. But for the racemic product molecule, the hydrogen atoms add from the same side necessarily, and that has to do with the mechanism, which I must admit that we can only give you kind of a hand-waving type of a mechanism. It's not a real like a fully characterized electron pushing mechanism per se. So, but let's say here's the palladium material that's deposited on the surface of charcoal. Say this is charcoal. This is sort of what we know happens. Hydrogen atom breaks up into hydrogen molecule breaks up into each atom. this on the surface of palladium or platinum, and then the alkene approaches, and when it does, something like this happens. Now, that didn't do a good job with that arrow. So that palladium neither total loses or gains electrons per se, and then when this happens, it happens in a concerted way. It's kind of like SN2 or E2, like everything happens in one step, right? So this is from the same sign. It's an addition. Now, this reaction is often used in the reduction of course, alkene to alkane. And that often results in more of a stackable molecule, because when you have an alkene, especially cis alkenes, they don't stack up on top of each other very well, which means they don't solidify very well at room temperature. And so for that reason, vegetable oils that tend to have a lot of unsaturation or double bonds alkenes in it, like this is a typical structure of an unsaturated fat molecule. This is often hydrogenated in the factory to make more of a alkane based molecule that's more stackable on top of each other, meaning it's more solidifying. And the reason why that's good for products is it's hard to spread your liquid vegetable oil, but it's easier to spread margarine, the solid, and so that's how they make margarine, is this reduction reaction, which, by the way, the unsaturated fatty acids that make up the triglyceride fat molecule here that is shown here, this is typical fat molecule structure. You might have heard about, in the context of healthy diet discussion, omega-6 versus omega-3 fatty acids. This is an omega-6 acid because the omega means the end of the fatty acid chain. 1, 2, 3, 4, 5, 6. There's a double bond that starts at the 6th carbon from the omega or the end. So this is omega-3 fatty acid. I shouldn't say W, but omega is like that. So I'm trying to draw this as a vegetable oil, but technically a vegetable oil would not have an omega-3 not being present. So that part is not very accurate about this structure, but once you do the hydrogenation, right, you're going to get more of a... I'm not going to be consistent with the number of carbons here just because I don't want to have to spend time counting the number of carbons, but what I'm trying to show, that's a horrible chain, is that it's going to be an alkane chain. Now, sometimes you're going to have palladium just relax the double bond, because cis double bond is a little bit of a less stable geometry than trans because of the sterics here, and so for that reason palladium can rearrange the double bond stereochemistry, and it can rearrange it to become trans geometry. Now that is very bad because all the unsaturated fatty acids in nature are cis geometry, and that's something we could deal with our enzymes to break it down for digestion, but our enzymes don't know what to do with trans, which is artificially created. So it accumulates in double bonds, as we'll see in this chapter. It's very reactive, it does a lot of things, and so this is going to cause some unwanted reactions that could lead to cancer and so forth. And so that's hydrogenation for you. Now, the rest of all the reactions we're going to cover in this chapter are a little bit different than hydrogenation, because hydrogenation is technically a reduction reaction. Maybe I should say that here, reduction. Everything else is kind of more of a either oxidation or neither reduction or oxidation type of reactions. Now, they're going to be all electrophilic additions, and what that means is the electrophile is going to capture the pi bond electrons. Okay, so here's a pi bond depiction. Remember that p orbitals have two phases like that, and then right, there's a side-to-side overlap, and between that, in that side-to-side overlap, they share 2 electrons. That's the pi bond, or the second bond in the double bond, ethylene or alkene, right? Because the pi electrons are shared only between the 2 orbitals, where there's only a loose side-to-side overlap, not like a head-to-head overlap of a sigma bond, right? These electrons are kind of loosely held. You could kind of picture, I don't know if this is an edifying example, but like little kids that are not very supervised very well by the parents, so to speak, right? What that means, though, and then, sorry, this is kind of a creepy analogy, but these pi electrons, compared to, say, sigma electrons, which are like more tightly supervised by the atoms or parents, so to speak, pi electrons are much more easily captured or kidnapped in a way. Because they're not as well supervised, or they're not as tightly held by the orbitals or atoms. Okay, so electrophiles, if you kind of think of them as pedophiles or something, if they're like looking for electrons to kidnap, the best ones, well, much better candidates would be pi electrons, not sigma electrons. So I hope that makes sense. And so here's the general mechanism. Sorry if I couldn't think of a more like edifying example here, but electrophiles can capture the pi electrons like so. And when it does, there's a geometric concern, right? Like the electrophile could end up on because you're using these 2 electrons to form a bond with the electrophile. Now, these 2 electrons are shared between these 2 carbons, so the new electrophile carbon bond could form here or there, right? There's 2 choices. But depending on where the electrophile ends up at, right, the carbocation can form either at the more substituted carbon or a less substituted carbon, and then you could probably guess which is more preferred. Because carbocation is severely electron deficient, it's better if it's surrounded by more electron rich atoms like carbons. So the more substituted carbocation is more preferred. So this less substituted version does not form. Okay, when I say that, what does not form is like if this is treated with some sort of a nucleophile, you might get this product, but we would call that the non-form, we would not consider that the normal outcome. The normal outcome is going to be the one where the nucleophile will attack that carbocation to form something like that, right? Because secondary cations are more stable than primary. Okay, so this regiochemical preference, remember regiochemical means like what part of the molecule. And that's called Markovnikov product. Okay, and what does that mean? That just means nucleophile on more substituted carbon in a electrophilic addition reaction. Now, you might wonder, well, if this is an electrophile dominant reaction mixture, where did the nucleophile come from? Usually these are weak nucleophile, like the solvent, like in the past we've seen in an SN1 or E1 reactions, right? The weak molecule like solvent, like alcohol, could act as either a weak nucleophile or weak base. It's kind of like that, okay? So we don't see this regiochemical preference, but normally, but we would call this the anti-Markovnikov product. Okay, So the take-home message here is that the Markovnikov reactions are preferred in all electrophilic addition reactions. Okay, so that's the theme. And then basically most of the reaction mechanism are going to be like this. So if you can master this, the rest of the chapter should be easier for you. Here's one example of Markovnikov reaction: is addition of some sort of hydrohalic acids like HCl, HBr, hydroiodic acid, stuff like that. And I hope it makes sense to you that within HBr, the electrophilic part is the H+. So the proton is our electrophile. This is going to be sort of our weak nucleophile that adds after as a result of electrophile adding and creating a carbocation. And the Markovnikov product is going to be the one where between these two double bonds, more substituted carbon gets the nucleophile, meaning that's going to be the product, which this is an example of a Markovnikov product. Okay, so let's try to explain that with the mechanism. So the HBr is the electrophile. Why? Because bromide is more electrophilic, and it's always thinking about leaving with those two electrons, right? So that's what happens, and then that would leave behind H+. Remember, H+ cannot exist all by itself, and so for that reason, it immediately grabs some other electrons, like pi electrons that are not very well supervised. Now, the result of that is going to be, you could put the carbocation either here or there. Of course, the tertiary is more stable, so the hydrogen is going to end up on this carbon. That's the new proton, okay? And we're not going to get that, okay? Now, what that leaves behind, of course, is bromide, which is actually a decent nucleophile, so it would add to the carbocation, and of course that's going to be the product. Okay, so that's the mechanism here. It might be helpful for you to think about this equilibrium. You could think of HBr as being in this dissociation equilibrium where the proton, of course, is our electrophile. Now, I want you to take time to think about the mechanism, but it's mainly the products. Here, I just want you to think of the products that you would get from this reaction. I will compare answers in the class. Okay, so please take time to do that. Another type of similar addition is you likewise use a strong acids like we did here, but we're going to use something like sulfuric acid, where remember the conjugate base of sulfuric acid, bisulfate, is a very bad nucleophile. It is not going to add even in an SN1 type of fashion. I want you to notice this is basically like an SN1 reaction here, right? And yet if we use a solvent that's weakly nucleophilic, that's the thing that could add Markovnikov. Okay, so that's this equation here, not equation, but the example here. Okay, so how does that work? Here, every time you see a reagent, draw it out always. Use structure of sulfuric acid. It's a strong acid. What do strong acids do? It's going to protonate something, in this case the pi bond or the double bond, right, by grabbing the electrophilic, the pi electrons. Technically, this is called the electrophilic attack. Maybe it doesn't seem like an attack because the arrow is not pointing to the thing that's being attacked, but if somebody came and grabbed your electrons, you might feel like you got attacked, right? You just got robbed, and that's what this is. Likewise, as before, the proton will be on the less substituted carbon, so that the carbocation will be on the more substituted carbon. Now, the problem, of course, is this is not nucleophilic. And so for that reason, what's going to happen is the solvent water that could attack that carbocation. And then from your studies with SN1 reactions, I think you know what's going to happen here, right? You get the positively charged oxonium ion, which could lose a proton with the help of like another solvent molecule. And that will get you to the product structure, which is indeed Markovnikov. So that's a hydration reaction. All right. See you guys in class or in the next video.